All right. Can everyone hear me? We're going to be starting very soon. So, get ready. All right. Very good. Oh yeah. So today, if you can tell, we're going to be learning quadrilaterals, which is going to be great. By the way, yeah, Alan, there is no homework in this class, at least not in geometry. Even though I think personally that math is very homework oriented, but Alan doesn't think so, so we're not going to do it. So yeah, so today we're going to learn quadrilaterals. Since last time we learned triangles, so let us start. So let me go ahead and start. All right. So what is a quadrilateral? So as you can see on the screen, we have a bunch of quadrilaterals here. We have all different kinds. They're all different kinds. And you might even see one here that's very funky. We're not going to go over this one, but it's called a convex quadrilateral because there is an obtuse angle right here. And it's basically going inward. So yeah. And by the way, I am talking. I'm not sure. But yeah. So let us start. So quadrilateral might seem like a pretty long word for a simple concept. It's pretty much just a shape with four sides, and that's pretty much it. If it has four sides, then it's a quadrilateral. Can everyone hear me? Some people can't hear me. Yeah, so maybe if you can't hear, yeah, just rejoin. Anyways, yeah, quadrilateral is a long word for a simple concept. It is a shape with four sides. So what does that mean? It means Latin, which is four, pretty obviously. Like triangle is Latin for three, so quad is Latin for four. So the thing is, you might think that adding one side to a three-sided shape was like very easy. So it was not really that important, but it adds enough complexity so that we're having a new slides and of course memorization. So triangles and quadrilaterals are pretty much the most important shapes. Oh, triangles, quadrilaterals, circles. We're gonna do circles next week. We're gonna do that, all three of these, and these are like some of the most fundamental shapes of all time. So you should probably know these, and there are going to be so many types, properties, and memorization. So just keep an eye out for that. And here are the most common quadrilaterals: parallelograms, kites, trapezoids, rhombi, rectangles, and squares. So those are all the basic types of quadrilaterals that you'll see. You might be able to see like this arrow shape in the corner, but mostly you'll see squares up here, parallelograms, rectangles, and trapezoids right here. Some people still can't hear. I'm not sure what's going on, but we're gonna just to confirm. Can other people hear me?
I can hear you.
Huh.
I can also hear you.
We're gonna move on, but hopefully that gets fixed. Yeah. All right. Okay, that's good. Yeah. Hopefully you didn't really miss anything because most of it is right here. But yeah. Most of these are just like the basic like categorizations, and there's like some people that say quadrilaterals have been almost classified to death because there are just so many properties, so many different types that you can make. So yeah, and we should probably talk about them first before we go into more depth. So this is the quadrilateral hierarchy. This is like kind of important to know. So at the very top, of course, we have the quadrilateral, which is any side with four shapes. And then we go into the three types. So there's going to be trapezoid, parallelogram, kites. Each of those have their own types, as you can see here. So we're going to go through pretty much all of these today. And so hopefully there's not going to be any questions. So this graphic is mainly just to say, oh, what are the most common types of quadrilaterals and how do we categorize them? And as you can see, all of these that are linked by a line, that means they're related. Okay, so for people that cannot hear, just turn it up a little louder. I don't know. I'm talking in my AirPods, so just like turn up your volume, I guess. And yeah, I do not have a camera set up right now, so yeah, because it's only temporary. Yeah, I don't have my teacher set up right now.
Wait, your camera's not open, by the way.
Yeah, I don't have my camera set up right now. I mean, I hope that's not a big deal. I'll set it up next time if I can, but I don't have it set up today, so that's not bad. Okay, so some quadrilaterals can also be called other names. So I don't know if people have taken geometry already, but some people have heard a square is a rectangle, but a rectangle is not a square. So you can see the square, it's at the bottom of all these classifications. That pretty much just means a square can be called a parallelogram, a kite, rectangle, and a rhombus, because it has all the basic definitions that you need. It just has extra properties. So it can be called a rectangle because it has all the rectangle's properties, but a rectangle cannot be called a square because it does not have the square's properties. And hopefully this helps like show how closely they are related and how it's easier to memorize. So first, let's talk about diagonals, because diagonals in quadrilaterals are surprisingly important. So a diagonal connects two non-adjacent points. So what that basically means is that if they're not connected already by a line, then you just connect that to another line, and that's a diagonal. So yeah, that just means if 2 points are not touching, they can connect by diagonal. So for example, A and C are able to form a diagonal because they weren't touching in the regular line. Whoops. And B and D are also diagonals. Diagonals in quadrilaterals are pretty important because sometimes you can immediately tell what the shape is with the diagonals alone. So yeah, diagonals also have special properties and they can help. So why are they important? Because diagonals can split a quadrilateral into triangles. So you can see here that this diagonal actually makes 4 different triangles in the shape. And we already learned about triangles, meaning we can derive many different properties. For instance, you can find the side of one of the quadrilaterals if you know the diagonals. So let us continue to the 3 main types of quadrilaterals: parallelograms, trapezoids, and kites. So here is the parallelogram. Here is the trapezoid. Actually, let's talk about these arrows. So like if they share the same amount of arrows, that means they're parallel. I think we learned this last week, but they share the same amount of arrows, meaning that the A and D are parallel to B and C. AB is parallel to DC because they share 2 arrows instead of 1 arrow. If they share 1 arrow, that means they're parallel. If they share 2 arrows, that means they're parallel as well. They're just different kinds of parallel. A trapezoid is right here, and a kite. So these are the 3 types of quadrilaterals. You really don't have to write it down, but these are the main types we're going to learn today. So let us start with a parallelogram, which is right here, right in the smack middle of the hierarchy. So the parallelogram starts out with 2 pairs of parallel sides. If a quadrilateral, meaning it has four sides, but the 4 sides have 2 pairs of parallel sides, no matter what it is a parallelogram. That's the only definition that a parallelogram has. If it has 2 pairs of parallel sides, then it is a parallelogram. So opposite sides, it just means opposite sides have to be parallel to each other. That just means like AD and BC, as well as AB and DC. So those have to be parallel. And opposite sides also have equal length. So this is kind of a proof, but if we have two pairs of sides that are parallel, then the 2 opposite sides will also have equal length. So AD is also equal to BC, and AB is also equal to DC. So if there are 2 parallel, then they have to be 2 pairs of parallel sides, and they also have to have equal length. And by the way, the diagonals also bisect each other. That just means the diagonals cut each other in half. So BD splits AC in half, and AC splits BD in half. That's basically just what it means. Not too important, but it is an interesting property that they share. So can you figure out this question? So we learned transversals. Hopefully you remember what they are. Given that one of the angles is 43 degrees, so you can see right here, one of the angles is 43 degrees. Can you find the measures of the other 3 angles? So we have 3 more angles here. We have 1, 2, 3. the other three corners have angles. So can you find what those angles are? So I'll give you like 2 minutes to find them. It's not too hard, but you can go ahead and try these. All right, so it looks like a couple of you have gotten it. And yeah, so let us go over them. So the answer. So given that one of the angles is 43 degrees, can you find the measure of the other three angles? So first of all, you would have to use transversals for all of them, basically, but let's try. So without loss of generality, that just means like we just restate what the problem says. So just don't worry about loss of generality. That just means we have already stated that B is 43. So angle B is 43. Notice that A and B are supplementary because since AD and BC are parallel, that means AB is the transversal, which means that this angle, angle B and angle A add up to 180. Therefore, angle A is 180 minus 43, which is 137. And then C is supplementary to B, so basically the same thing. AB and DC are parallel, and BC is the transversal, which means it cuts this in half, meaning that angle B and angle C are supplementary, which means that C is also 137. So we can find out that it's using the same thing for D. So A is 137, B is 43, as we said, C is 137, and D is 43. So yeah, good job to everyone that got it. I'm pretty sure like everyone got it. So yeah, good job to you guys. That's pretty much how you do it. You just use parallel lines and stuff to figure it out. So yeah, so now we're moving on to the rectangle. So the rectangle is a subset of the parallelogram. So it's right under parallelogram, which means that it is going to have all the parallelograms properties. So like it has opposite sides have equal length, opposite sides are also parallel. And yeah. So a rectangle is a quadrilateral, but all its angles are equal. It is a subset of parallelograms, which means it has all its properties, except it has new properties that make it different. So that just basically just means it has equal angles, which is 90 degrees, and the diagonals are equal length. So yeah, the diagonals have equal length, and they still bisect because parallelogram diagonals also bisect. So rectangle diagonals also bisect, but they're also same length now. Okay, so that's sort of interesting, but what's more interesting is something that we use a little bit in competition called the British flag theorem. Using the name, I'm pretty sure it came from the British flag. So we're gonna see how it works. So let's say we have a rectangle ABCD, right? So we have a rectangle like this and a random point P inside, anywhere inside this rectangle. So let's just put P right here. And now we put all the vertices to P. So now we have this kind of weird shape that splits the rectangle. So what the theorem is PA squared, so P to A squared plus PC squared, so the length. So let's say PA was like 3 and PC was 4. And let's say PB squared plus PD. So basically this squared, PA squared plus PC squared equals PB squared plus PD squared. So if I gave you PA, PB, and PD, you could probably find what PC is. So you could use Pythagorean theorem to solve to prove it. You can try it on your own. You just have to drop down the altitude and then probably just find it. But we're not gonna prove it today. It's a little lengthy and I don't want to bore you with the details, but just know that it works and it has been proven. So let us start with a question for rectangles. We're not gonna do the Birch-Flag theorem question. It's a little out of some people's comfort zone, but we're gonna go over this. So can you find the diagonal of a rectangle if I know that the side lengths are 5 and 12? So can you find the diagonal of this rectangle? So I'll give you 3 to 4 minutes, or 2 to 3 minutes. All right, so it seemed like it wasn't that hard, so we're just gonna go over it, and let's see if you got it correct. So let's just draw the diagonal and see if it will help. So just using Pythagorean theorem, also we can use another property that opposite sides are equal. So we can just drop this 12 down to this side. So we can bring the 12 down to this side, and we can use our Pythagorean theorem to solve it. So 5 squared plus 12 squared is 169. And if you know your math, then you should know that 13 squared is also equal to 169. meaning that the diagonal is actually equal to 13. A squared plus b squared is c squared, and since c is 13, we know that the diagonal is plus 13. And since diagonals are equal, the other diagonal is also 13. And they also bisect, which means they'll split each other into half. So yeah, so now we can see how diagonal can be used to split it into triangles and how we use the Pythagorean Theorem, which is a triangle property to find something from a quadrilateral. Something very interesting. So, yeah, so math is always fundamentally linked, which is always pretty interesting. All maths are, you will use from pre-algebra all the way to calculus, you'll use all the same properties, and this is just one example of how this works. You can use triangle properties to solve quadrilaterals. Pretty simple. The next, we're gonna not go to square, but we're actually gonna go to trapezoid, because trapezoids are also very wacky inside the quadrilateral family. Okay, so here we have the basic trapezoids. I think most of us will use scalene and isosceles, so the based on size ones. So these two are the ones that we mostly just use. Sometimes we use a right trapezoid, and we don't really see obtuse and acute trapezoid. We don't see obtuse that much, and acute trapezoid is the one we typically see. So yeah, so I think these four minus the obtuse trapezoid are most important. So yeah, just keep in mind out for those. So in this class, at least in this geometry class, we will define a trapezoid as a quadrilateral with exactly one pair of parallel sides. So some people that will say, they will vehemently say that it will have at least one pair, meaning that rectangles are technically trapezoids. But most of us that look at a trapezoid like this, or look at a rectangle, when we look at a rectangle, we will never say, oh, that's a trapezoid, because I don't think most of us think it like that. There are controversies that some people will say rectangles, squares, parallelograms are trapezoids. I don't think so. Most of you probably don't think so. So we're gonna set the record here, and we're gonna say it has exactly one pair. No more, no less. It has to have only one pair and one pair. So as you can see, all these trapezoids here have one pair. So the first one has one pair, the top and bottom, and also have top and bottom parallel. So there's some terminology you should probably know, is that the non-parallel sides are called the legs. So basically the side ones that are angled are the legs, and the top and bottom are base, the ones that are parallel. So the top is a base, bottom is a base, the top of this is a base, BC is a base. Yeah, same thing basically. And there are two main kinds that we will talk about, at least in this class: isosceles trapezoid and scalene trapezoid. So if you remember from triangles, isosceles just means that they have two equal sides. So if you infer with your big brain, you might also say, hey, this also has two of the same legs. And for scalene, that just means all the sides are different sides. Not all the sides, but the legs are different lengths. So you can see the first one, A, B, and DC have different lengths. So one of them has one line, one of them has three lines, meaning they're different lengths. Okay, so using very tricky maths, can you figure out the height of the trapezoid? So okay, let's see if so can you figure out x for this question? So let me give you a hint. You can use Pythagorean theorem to figure it out. And by the way, we're not going to be learning area. I think this week we're going to be learning area, a separate class. So yeah, just don't worry about area for now. Just find the height and we'll be good. All right, so several of you have gotten it, meaning we can go ahead and attempt this. Okay, so at first pass, this might seem very impossible because you probably don't know the length of any of the other sides. You can't use any input information to try to find it, but there's an important thing that you must note. Is that you can drop another side, another height down like that, and you could try to find, you might recognize it and you might see, oh, it's a rectangle because the height is perpendicular to the base, meaning that it's going to form right angles right here and here and here and here, meaning it's a rectangle, meaning the opposite sides are equal, meaning that this is actually a side of 3, and this is also 3 because it's isosceles, meaning they have the same sides, which means they're equal. And this, of course, adds up to 9. So 3 plus 3 plus 3 is 9. So this is all correct. And you might say, oh, so if this is 5 and this is 3, then x is what? Well, since this is a right angle, you use Pythagorean Theorem. Simply find that, well, 5 squared is 25, minus 9 squared, which is 3 squared, equals 16, is 4 squared. So x is equal to 4. And if this was a harder question, I would have asked you, oh, what's the area of this trapezoid? But we're not doing area this week, according to Alan, so I'll let you guys go on that one. So you can use Pythagorean Theorem to find that it is indeed 4 using Pythagorean Theorem. So again, we have used triangle properties again to try and rectangle properties to find the height of a trapezoid. So we have used many different things that we've learned from all different types of math, well, mostly just triangles and quadrilaterals so far, to find the height of something that seems completely different, completely random. So that's basically what math is all about. So I think right now is around halfway. We're done class. So I will give you guys probably, let's see, I think you guys deserve 5 minutes. I guess to have a break and I guess be back by 8:35, 8:36. So see you then. Okie dokie. Yeah, I think that's good enough for a break. So we're going to continue. After trapezoids, what do you think will be next? Well, let us see. Oh, a kite. So we've done trapezoid, parallelogram, rectangle. So let's do kites. So this is not going to be like your childhood kite. I know some of you might have had a kite before, but we're not going to be doing that today, unfortunately. We're going to do kites, and kites are also some weird shapes that we don't really see that often in geometry, just because they're kind of weird and they're not really that important. I would say, but they do have some properties that we should probably go over. So a kite is a quadrilateral with two pairs of adjacent sides equal in length. So it has two pairs of equal length sides. You could say, oh, that's a rectangle, but this is adjacent, meaning that the sides that are next to each other share equal sides. So that just means IT and TE. So these two sides, the bottom two right here, share one side, and then KI and KE, so those two sides that are next to each other, the top two, share the same length. So yeah, so it just has two pairs of adjacent sides in equal length. And what's interesting is that its diagonals are always perpendicular. So KT and IE are all perpendicular. And what this means is a hint, Pythagorean theorem. And you might see KXE, see this triangle right here? You can see this right angle, see the triangle, meaning Pythagorean theorem. Anytime you see a right angle and triangle, usually that means Pythagorean theorem. So in this case, it does. So for instance, if I gave you the length of this diagonal, these diagonals, you could probably find the length of all the sides because you can use Pythagorean theorem. Another instance of a right triangle and a right angle in a triangle will be similar triangles. Similar triangles are very important in math. But we're not going to be doing similar triangles, at least not in this class. So don't worry about it. And fun fact: the longer diagonal. So in this instance, KT. So this long one bisects the shorter angle, the shorter of the diagonal, so IE. So that means this this long line just cuts this short line in half. That's just what it means. All right, so now we're going to be going on to the special quadrilaterals. So I mean, the only thing special about them is that they have like the previous quadrilateral properties. So I'm talking about the rectangle, rhombus, and square. We already went over the rectangle. But now we're going to go over the rhombus and the square. And these are very special because they share all the special and cool properties of the previous shapes. So I've already said that, but it just means that if these are connected, that means they're probably related. So let us see one example. So one of them is the rhombus. So rhombus is not that well known, I think, especially for beginners, but it is like pretty important. Because not a lot of people know them. Some test takers will put them in just to troll you, and they'll be like, "Oh yeah, remember this shape that you probably never used before? Yeah, we're gonna put this in the test and see if you remember any of the properties." So yeah, that's usually what happens. Kite and rhombus. So those are the two that are very obscure but very important. So just make sure to remember those. And yeah, as you can see, the kite is both a subset of the parallelogram and the rhombus. I mean, the parallelogram and the kite. So it shares properties from these two. So it is a subset of parallelograms and kites. It is a quadrilateral of equal size. So as you can see, we're slowly approaching square territory. So now we have that they have all the same sides. So AD, AB, BC, and CD all are equal sides. And for the rectangle, we saw that they all have equal angles. So guess what? Next is square with equal sides, equal angles. Okay, but another interesting thing is that the diagonals of a rhombus bisect each other and are also perpendicular. And guess where we heard that from? The kite, because the rhombus is a subset of the parallelogram. So it has bisecting and perpendicular diagonals. Hint, Pythagorean theorem again. You can use Pythagorean theorem especially for this because they bisect each other. So if I gave you like that this is equal to 8 and this is equal to 6, you could find the length of all the sides, which is fine. And dang, okay. So I was supposed to put transitions, and I was gonna have someone tell me what it is, but there's a the name for the multiple rhombuses. So you don't say rhombuses, even though most people say also rhombuses. But actually, if you want to say multiple, you would say rhombi. The answer's here, but fun fact. So someone asked you, how do I say multiple rhombus? You would say, oh, rhombi, because English is weird. So yeah, don't say rhombuses, it's wrong. It's rhombi. Square. So now we have finally reached the epitome of all quadrilaterals. This is the big daddy, as some people say. It is very important, especially in geometry. Has many interesting, many properties and many problems where you take advantage of this and try to trick you. So first, let's go over this property. So this is going to be a handful, a mouthful. So watch out. So a square is a subset of every quadrilateral that we talked about, except for isosceles, trapezoid, because trapezoid is weird, and we're not going to talk about that. So it is a parallelogram. It is a kite, a rectangle, and a rhombus. It has all the properties, every single one of those. So you would ask, oh, are the sides parallel? Yes, they are. Are the angles equal? Yes, they are. Are the diagonals bisecting? Yes, they are. Are they equal? Yes, they are. So let's go over them. So a square is a quadrilateral with all the neat properties that we just talked about, except for trapezoids, of course. It has equal sides, equal angles, equal diagonals. So all the sides are equal. All the angles are equal. They're 90 degrees. And the diagonals are also equal length. So yeah. And they also are perpendicular. So that just means that they have a 90-degree angle. So you can see many 90 degrees happening here. So there's one here and one here. Similar triangles alert. And we have parallel sides. So AB, CD, BC, and AD. All those fun stuff. So yeah, that's pretty much, I think those are all the properties. If not, then you just go back and check all of them. But yeah, it's a mouthful. Has every property you can ever imagine, which makes it a very useful shape. So last time we learned about equilateral triangle, and with that we learned it's a regular polygon. Well, since it has equal size and equal angles, that means a square is also a regular polygon, just like the equilateral triangle. I'm not sure if it's on here, but technically, since it has equal sides and equal angles, since we have the equilateral triangle, we can call a square the equilateral equal angular quadrilateral. You could say that if you want to be fancy, but we're not going to be fancy today. I'll type it in chat actually. Equilateral equiangular quadrilateral. You could technically call it that, and you'd be correct. You'd be like a massive nerd though, and no one would like you. But you could call it that, and you would be correct. So this is, I guess, a pretty simple question. If I gave you a square with length s, could you find the diagonal in terms of s, of course? So yeah, anyone who does any amount of tricks should know this instantly. But guys, I guess like 2 or 3 minutes to try to solve it. So yeah, anyone that does trick instantly should know this one. If not, Pythagorean Theorem. All right, we can go on. We're a little bit ahead of time, but it's fine. We can cut off a bit early. Quadrilaterals are very long, so I don't want to continue boring you with the details, but let us continue. And let us see. So for those who didn't know, you could use Pythagorean Theorem for this one. And how would you do that, of course? So first you would like list it out. So let's just, without loss of generality, let's just have the sides S, as you can see here, and the diagonal D. So let's just write it, S squared plus S squared is D squared. Nothing too funky here. 2S is equal to, well, 2S squared is equal to D squared. So everything's normal. We just added the S squares together. And finally, well, how did I get from step 4 to step 5? You might be asking. Okay, first I switched the sides around. Nothing too fancy there. 2 equals 2 and 2 equals 2, or X equals 2 and 2 equals X. Like there's no difference there. But what I did is I moved the sides, and then I square rooted both sides. So I just want to find what D is equal to in terms of S. So diagonal, which is the diagonal, is equal to S square root 2, because I squared the sides. So S squared square rooted is S, and 2 square rooted is square root 2. So every single square with side S will have diagonal S square root 2. And for instance, if the square had side 1, you would have 1 of square root 2. If you had a side of square root 2, then the diagonal would be 2, because square root 2 times square root 2 is 2. So if the side was square root 2, then the diagonal is 2. So yeah, for those going through trig, this is one of the most important relations for 45, 45, 90 triangles. Memorize this. So for, I guess, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So those angles just it's just S squared. S is square root 2 over 2. Just that's important. So yeah, nerd talk. Don't worry about it. Okay, Cyclic Quadrilateral. So that's basically the last thing we're gonna go over today. So you might be thinking, oh, we just finished squares. How else can we go from here? Well, I didn't tell you about something called Cyclic Quadrilateral. So this wasn't part of a hierarchy, which means it's like its separate category. So it's not going to be really part of the main few. So Cyclic Quadrilaterals. So what are they? So are they quadrilaterals that cycle? Are they cyclic? Yes and no at the same time, and you'll see why. Okay, so this is a long paragraph, but I will make sure to go through it quick and simple. So these cyclic quadrilaterals are quadrilaterals that just have a circle around. So as you can see here, we have this quadrilateral A, B, C, D. The only thing that makes it different from another quadrilateral is that it has a circle around it. So a circle will touch all of its points. It will not go inside. It will never go inside the quadrilateral, because that's wrong. You can't do that. It has to stay outside the quadrilateral all times, only touching at the points. So that's an important distinction to make. And why are we talking about this? What is so interesting about circles around quadrilaterals? Well, they have very interesting properties, and even this very important theorem that you should probably know that will make all this worth it. So important distinction number 2, not all quadrilaterals are cyclic. So if you make a some quadrilaterals will never be cyclic. For instance, if you make a very, very thin rhombus, it's almost a line, you will never be able to make a cyclic quadrilateral. So let me see if I can find it. Okay, so let's see, will this work? So yeah, if you look at this very thin rhombus, if you try to trace a circle around it, you won't be able to touch all the points. You will only be able to touch these, like the top and the bottom points at most. And if you try to touch all 4 points, you'll create an ellipse, and that is not correct. So it has to touch the points only. It cannot touch the sides. It cannot go inside the quadrilateral. It has to stay outside at all times, and it has to only touch at these points. Okay, so what kind of properties do they have? Well, here's a spoiler alert for those that already see it, but don't read this. Don't read this. I'll go through them. So the first one, opposite angles are supplementary. So A and C and B and D. So A plus C is 180. B plus C is 180. They are supplementary, and you can use I guess this to figure it out. I think you can use PowerPoint. No, you can't use PowerPoint, but you can. This is just a theorem. So A and C are equal. I mean, A and C add up to 180, and B and D also add up to 180. And adding multiplication of opposite sides equals a part of the angle. So that's the next theorem. We're going to be learning that right after. So don't worry about number 2 yet. And every rectangle and every isosceles trapezoid is cyclic. So if you make any rectangle, any quadrilateral with 4 right angles, you will be making a cyclic quadrilateral. So as much as you try, you will always be making a rectangle that will always be cyclic. So even if you make the thinnest possible rectangle, it's very possible to make a very, very big circle to go all the way around, and it'll still touch all 4 points. So every rectangle and every isosceles trapezoid is cyclic. If you're wondering why it has these first 2 properties, which makes them equal, which makes them a cyclic quadrilateral. So these are the 3. Right? These are the 3 properties of cyclic quadrilaterals, and these are very important, and you'll be able to use them later on. For instance, there's this thing called Ramagupta's theorem, which you can find the area of a cyclic quadrilateral using the sides only. And the next one is Ptolemy's theorem, which uses the sides and the diagonals to find you'll see. So I will not go over this. The Ptolemy's theorem. So Ptolemy, I think we introduced him day 1, but he was a Greek astronomer, so that's mathematician. And he basically was very important. So here's the theorem. This doesn't really mean much to you. I mean, I guess you could write it down and draw the picture if you really want. But let's go over it. So this is a property unique to all cyclic quadrilaterals only. Technically, cyclic quadrilaterals meaning all rectangles and all isosceles trapezoids. But yeah, so all to cyclic quadrilateral only. If it is cyclic, then it has this property down here. So if you have AB, the 2 sides opposite each other. So AB and CD, they're opposite on this circle, opposite sides. If you add them, and so AB times CD plus AD times BC, so the other 2 opposite sides. So the first 2 opposite sides times each other, then the other 2 opposite sides times each other equals AC, which is the diagonal, plus times BD. So this means the 2 opposite sides multiplied by each other, and then you add them, equals the diagonals multiplied by each other. We don't see this theorem often, but when it pops up, you'll be catched by surprise. So you should probably memorize this. It's not too hard to memorize. So you should probably just memorize it anyways. And again, we can see how important diagonals can have on shapes. So here it is again. Diagonals have an important property on fundamental shapes. For instance, a cyclic quadrilateral. So do not doubt the power of diagonals and the power of triangles. Yeah. And it was used actually in real life. It was actually used by Greek astronomer and mathematician Ptolemy, and he used it in his charts to help him find stars. So yeah, this isn't some random theorem that you can't apply ever. If you were an astronomer like Ptolemy, you could use it, and you can use it to find stars, and you can use it to basically help mankind to where it is today. You can use it to send people to Mars. I don't know, pretty much anything you could think of. So you could prove it. It would take someone with immense brain power. I don't know how to prove it. But according to Alan, you have to use equilateral triangles as a corollary, and we really won't be using that. Corollary just means a precursor to a theorem. So like if you're trying to prove like some humongous IMO problem, like international mathematician, you would start with very basic shapes. So like 2D shapes, work your way up to 3D, and then maybe 4D. So it's a corollary, and we won't be proving that here today. It would take immensely long, and it would probably make no sense. So just know that this property does work. It has been proven, and it has real world applications, which is why I'm telling you this, in case any of you want to go to astronomy, be inspired. So yeah, this is the property, and I think that should be it. So that is it for today. This is the final slide, I think. Yeah, this is the final slide. Yeah, if you have any questions, email this dude. This is Alan, and this is Jonathan. Yeah, and for everyone, I'll send this. I think Alan will send the slides to you guys because I don't have your emails. So we'll send the slides. Hope you learned something today. If not, hope that you were, I guess, learned a little bit. But yeah, that's it for today. If you don't have any questions, then you can go ahead and leave. Have a good day, and I'll see you in the next class. I think I'm teaching next class at least.
Instructor.
You have a question?
What?
You have a question?
Yeah, can you please send the last few classes, like these pages, to my mom, like cos with her email is cosmicpw@yahoomail.com.
Got you.
I wasn't here for the last few classes because I was on a road trip.
That's fine. Which class do you want?
Just the last few classes that you have like teaching.
Send all the classes to you.
What?
I'll send all of them to you. Don't worry about it.
Okay, thanks.
My pleasure. Just
Bye.
have a good one. See you next week. The rest of you don't have any questions, you are free to leave. See you, son. Well, pretty sure the rest of you do not have any questions and you are probably not here. Go end the class and I'll see you next week.